So if we do nothing about climate change, we're looking at saying somewhere around 900, 1,000 parts per million carbon dioxide. That's if we do nothing. Okay, so that's going to have an impact. I'm quite confident of that, and I'll show you results of that. Because that's one scenario we'll do, and I'll call that RCP 8.5. I want to explain what that means, but it's going to be RCP 8.5, and I'll call it business as usual. Okay? We also have our current COP21 Paris Agreement. Okay, so it's actually a very weak agreement at this stage. It's certainly a step forward, and there's some, maybe some of you followed in the news even this week, there's some European countries that have now pledged to actually ratify the COP21 agreement. And here's what's hoped for. Okay, so we're hoping for about 2 degrees. Okay, people are talking about 1.5 degrees. I personally see that as unrealistic, but 2 degrees I think would be a good target. And at 2 degrees warming, we don't really add very much more carbon dioxide to the atmosphere, maybe 475, 450. Okay. So we'll probably have somewhere in between here, right? So somewhere between, say, 450 and somewhere in 1,000 parts per million of carbon dioxide in the atmosphere. Okay. So how do we know which one we're going to take? Well, we don't. Okay, so what we do is we run the model for different scenarios. We run it for our mitigation scenario, we run it for our business as usual scenario, and we run it for everything in between to see what we get. Well, this is a picture, again, so now we have a historical climate, 1850 to 2000. These are 42 models from the IPCC report. That some of them are the same models, just running in different configurations. And you can see that the models do a really quite a nice job of capturing the observations with the big line there. Okay. And there's our current temperature. I should say current. That's the IPCC, even though they came out in 2013, they were using 2005 as the current temperature. Okay, so using 2005 levels. Here's what we can expect in the future. This is from 2005 to 2100, and we see quite a bit of spread there. Okay. That spread is really our range of possible futures. Okay. What we do today will impact what we have at the end of the century. That spread is roughly about 1 to 5 degrees Celsius, and that all depends on the scenario that we take. Okay, so that's that business as usual scenario. This red line right here is business as usual. And we have the RCP. I like to look at this as the Paris Agreement level right there, which is about 2 degrees. Okay. It's the Paris level there. Okay. You can see those right there, RCP 4.5 and 8.5. We have 3 to 5.5 degrees. Okay. Remember that previous plot where I showed 10 meters of sea level rise? When I said about 5 degrees warming, it was really more like 4. But it was, say, 5 degrees warming globally resulted in 10 meters of sea level rise. It takes a long time to get to that 10 meters, so we won't see that at the end of the century. We might see it for 1 meter or something like that. But over time, we might see 10 meters potentially sea level rise. Okay. This is just the regional, these are regional projections of climate change. Okay, so 2081 to 2100, and this is the business as usual scenario, RCP 8.5. Okay. We see most of the warming is projected over land. And this is RCP 4.5, the mitigation scenario at the end of the century. Okay. Here we have the same 2 scenarios, but from 2016 to 2035, which just started this year, right? 2016 to 2035, this is the warming we can expect there. Notice that in the business as usual scenario, between the business as usual scenario and the RCP 4.5, or the mitigation scenario, we see very little change in mid-century. Right? So what we do now won't make much impact in some sense to 2050, but it will make an impact at the end of the century. We see very large differences between these at the end of the century. We see emissions that are cumulative, building up in the atmosphere, and stay there for a long time. And so over land, we're getting changes of 3 to 10 degrees warming. Okay, so when we say 2 degrees, say with Paris, that's globally, and that counts the ocean temperatures, but that's really like 3 degrees over land. So we should think of that. I like to think of that as more like 3 degrees over land, 1 degree over ocean, 1 degree over ocean. What did we get in Central America? I showed this plot last time, so if any of you were present. Okay, and this is temperature change for Central America. And you can see, again, this is using the global model, so our resolution is quite poor, so we have to kind of step back and look at this. But we're getting something on the 4 to 5 degrees warming by 2100 in Central America. And that was under the business as usual scenario. If we do the mitigation scenario, we're looking at something like 2 degrees warming or so. Okay, so we really have a lot to stand to benefit quite a bit if we mitigate on the impacts of climate change. Precipitation, drying, so we're hotter, drier climate that's climate change window, that would be what's called a hotspot, where it's hotter and drier at the same time. Those two feed each other. It's called a positive feedback. Okay? So it's like I think maybe a common language would be like a vicious cycle or something like that. It's a positive feedback. Those two feed each other. So the drying causes more warming and so on. And Central America and also parts of North America, the Southwest U.S. and Mexico, most models are projected to get drier and hotter. Again, this is a very coarse resolution, so how can I really trust these? I mean, if these models aren't even really resolving coastlines properly and so on, I can't really trust them at a local scale. In El Salvador, we can't trust them. I can say with some certain degree of confidence that Central America would be hotter and drier, but I can't say with much confidence that El Salvador, in particular, or San Salvador, would be hotter and drier. Let's look at the global. So before I get into regionalizing these projections, let's look at the projection of sea level rise. Here's our current sea level, and here are our projections. And we're looking at anywhere between 0.5 and 1.2 meters of sea level rise, depending on the emissions path that we take. Okay, so if we do mitigation, we're still looking at over 0.5 meters of sea level rise. Not a big deal here in San Salvador, but it is a big deal down in the coastline. Business as usual, about a meter of sea level rise. Just to look at sea ice extent. Okay, this is our mitigation scenario. So I'm flipping this. This purple or violet line, lavender, is where the sort of current sea ice extent is on average. Okay, and this is where the mitigation scenario shows it will occur. So we actually have ice, will have ice year round, or lack of ice year round, so we could actually have shipping channels in there, and so on, that, so that we won't have full coverage of ice with the mitigation scenario. If we look at the business as usual scenario, we won't have any sea ice. Okay? I think it's quite a shocking plot. Warmer weather is great, right? Yeah. Maybe not for you guys, but we all love, even in Los Angeles, which is a pretty warm place, we just went through a heat wave right now, and I think pretty sure everybody liked that warmer weather. We like it if it's a little warmer. John and I can go surfing without wetsuits. And but I know here you're not really interested in warmer weather. So, but I think some people, at least in the Western world, Northwestern Hemisphere, aren't too concerned about having a warmer climate. We all want it to be a little warmer. We all like it when it is warm. Okay, so let's look at the impacts of warmer weather on our various sectors. Okay, so we have warmer temperatures, we have changes in precipitation, so some areas might get wetter, some will get drier. Okay, on average, we get more precipitation globally, but there are regions like El Salvador that would potentially get drier, which has some impacts on, say, agriculture. Sea level rise. Okay, so these three factors cause a different, they impact our various sectors. One is they have health impacts. If they get the Zika virus, then mosquitoes, okay, their habitats can change. If it gets wetter, warmer, they might expand north and south. Okay? If it gets drier, then their habitats are decreased, which is a good thing for them. But if it gets drier, that has negative impacts on agriculture. Okay? If it gets warmer in Canada, that's great for agriculture. So there's some impacts. Forest impacts. Okay? Trees have to move up higher mountains. Okay? But we run out of mountains, right? When we get to the top of them. But they have to maybe move up higher. Water resources impacts. So this is sort of my area here. I'll show up on the slide on that another time. Okay? And the impacts on coastal areas. Obviously, sea level rise will have an impact on coastal areas and the temperatures as well. And then the species and natural areas, which are really pictures. Okay, so how do we get useful information at the scale of, say, San Salvador? Well, we can use something called a regional climate model. Okay, what does a regional climate model do? Well, it's a nest. It basically nests it inside of the global model. Okay? And this is the global model resolution. If anybody's familiar with, say, Mexico, okay, we know that there's no channel right there, right? Okay, so there's, it's not the Panama Canal there. And, but these global models are saying that there is a channel there. Okay? And there's no Baja California, if anybody's familiar with the geography of Mexico, okay, or no Florida. So we then run we nest in a regional climate model at a very high resolution. And we can see now we have no channel there. We have it's Baja California, very nicely resolved, Florida, very nicely resolved. So we run this nested model at a very high resolution. And we can run it at, say, kilometer scale. It's not 1 meter, but now we're running at a scale of, say, 1 kilometer in a very ideal case, or 10 kilometers, which is good, 15 kilometers. Most of the runs I do are around 15, 20 kilometers. And when we have that scale, and we can say these are watersheds here. And now we can start to think about the impacts of climate on various sectors. We can look at food, health, agriculture, water resources, ecosystems, and storm surface, and things like that. And these are there's so many things you can look at in terms of impacts. You can look at flood, drought, water resources, energy, agriculture, land cover change, biomass burning, some of that as well, pollution, human health, fisheries, ecosystems, and just take the output from these models and we drive what are called impacts models. So that brings me to the next part of the talk, which is really talking about this human adaptability threshold. And I'm going to use a variable called wet bulb temperature. Okay. How many are familiar with wet bulb temperature? It's a direct translation in English. Okay, you are. Okay, I'll explain it because I wasn't expecting to answer. Temperature to which air would cool if water were evaporated into it until saturation of the constant pressure. So if we take this room here, we start injecting water into it, start squirting water into it, it's going to evaporate into the air, and then we're going to reach saturation. As it reaches saturation, the air cools due to evaporative cooling. Right? So we start to cool down. When we reach saturation, that is called wet bulb temperature. Two scenarios here. Okay, so we have a dry bulb thermometer. So our standard thermometer is called a dry bulb thermometer. Okay, so that's just the thermometer you take your temperature with when you're sick, or the temperature we measure with the weather reports. And we have two scenarios, one with high wet bulb temperature and one with low wet bulb temperature. And you wet the bulb of this thermometer. And you just pass air across it. It's actually called the old way to do it is a sling cyclometer, or word for it. And you pass air over it and you cool the temperature down. So if you have a very hot and dry climate, okay, so we're going to be talking about the Middle East here. And most people think of the Middle East as a very dry place. Right? So we expect actually very low wet bulb temperatures. Okay? Southern California, very dry place, we have low wet bulb temperatures. So we have hot, it's hot, but then we have very dry air, that wet bulb temperature will become much lower because we can evaporate a lot of air, which causes cooling. And you can have a humid place, like here, and today, we have probably, the wet bulb temperature is probably very close to the dry bulb temperature. Anyway, the point is that wet bulb temperature is a combined measure of temperature and humidity. A higher wet bulb temperature means we have very hot and humid conditions. That's bad for human health. Hot and dry we can deal with. Our bodies can deal with that. We can perspire and we can cool ourselves down. But hot and humid conditions, our bodies cannot deal with very well. Okay? We have various cooling mechanisms of the body. I'm not going to get into this very much, but our body, so it's taking the temperature, you have a normal temperature at 37 degrees. Okay, so you put a thermometer in your mouth or in your armpit or wherever, you can get 37 degrees for core temperature. Many of you don't know is that our skin temperature, the temperature on our skin is about 35 degrees. It's a little bit cooler. That's why you don't put the thermometer on your hand, you put it in your armpit so you get sort of more in the core area in your mouth, in the US. And that temperature gradient, so 37 to 35, will drive heat off the body. Okay, it causes cooling. So our body's trying to always regulate our temperature at 37 degrees. In warm conditions, warm ambient conditions, we got to cool down. Our body expends energy to cool themselves down. Now, if wet bulb temperature, though, if you remember, wet bulb temperature is always lower than the dry bulb temperature. It's less than or equal to the dry bulb temperature. So if we have a temperature of 35 degrees Celsius at our skin, wet bulb temperature, our skin, the second law of thermodynamics says that our body cannot shed any more heat. Okay, we can't evaporatively cool, so no perspiration won't work, and no evaporative cooling. No conduction, no radiation. In fact, the temperature gradient reverses. Our body will overheat in 6 hours, even for the fittest of humans will die in less than 6 hours. Okay, someone like me, maybe 20 minutes. Maybe less. Okay. And so I think, I'm not sure if you have anything like this in El Salvador, the meteorological service here. But we in the US have something called the heat index. Some people see something called the feels like temperature. That thing's called. And 35 degrees Celsius is a very, very warm wet bulb. It's a very high temperature. It doesn't seem like it because we might, I don't know how warm it is today. Maybe it's 32 or something. It's not that warm. But the wet bulb temperature is much lower than that. Maybe it's 25 today or something. Okay. According to the National Weather Service, that heat index, that feels like temperature, or whatever you use, is something like 77 degrees. So some temperature we've never approaching boiling at that point. Okay? So it's something you wouldn't think we'd ever see on Earth. But just to give you an idea, though, 31 degrees, wet bulb temperature of 31 degrees is what the National Weather Service, our U.S. National Weather Service, says is extremely dangerous. Okay, so we should be in air-conditioned conditions, like this room here. We should be out of the sun, well-ventilated conditions. Otherwise, we're at risk of heat stroke. Okay, so where on the globe do we see? This is the first step of this analysis, was to look where on the globe we saw high wet bulb temperatures. So we see values of, we're just showing this plot here, 27 to about 32, and you see values of approaching, this is just the maximum wet bulb temperature and a record of data that we have is from 1979 to present, and you see values approaching, say, 31 degrees. Okay. So we see this dangerous threshold, extremely dangerous threshold of wet bulb temperatures, but we don't see anything hitting this 35 degrees that we're talking about here, which will cause mortality. So what we did in the set of experiments is we focus on these two regions. One is this Middle East region here, okay, which includes some of Iran, and South Asia. Okay, so I can't really show much for the results from South Asia, although those to me are the more interesting results. But I think these results here are extremely relevant as well, because there are certain rituals in the Middle East that require people to be outdoors during the summertime, called the Hajj, or the Muslim pilgrimage. Okay? But we see in the nature that 30 degrees is rarely exceeded. Again, this is just the worst wet bulb temperature event on record from 1979. Okay? And what we see is also the Red Sea, Persian Gulf, okay, they call it the Arabian Gulf. And the Indus and Ganges valleys are very vulnerable. So we have the Indus Valley here, okay, in Pakistan, in parts of India, and then the Ganges Valley here. Okay. Those are vulnerable regions. So the hypothesis is under climate change scenarios that we might exceed that 35 degree threshold in the future. And when we started this work, and I'm going to tell you right now, we do exceed that threshold. When we started this work, we were expecting just the results would be that we are approaching the threshold, so we're not exceeding it. But it turns out we have exceedances, and it turns out last summer there was an exceedance in Bandar Mashar in Iran. This is the Southwest Asia. Okay, we have the Persian Gulf here, the Red Sea. Okay, you can see the lights here. This is generally a very rich region. It import a lot of workers from Pakistan. But we have Yemen here, which is actually a very poor region. They don't have the oil that the rest of the regions that have. Population is growing extremely rapidly there. There's the highest population, one of some of the highest population growth rates globally. And before I move on to those results, I want to show you South Asia, which is why I think this is more interesting, because it's not rich in the adaptability capacity is not as high as they are, say, in the Persian Gulf region, where you have access to air conditioning and energy. This is a plot of population density. Okay, so we just took population density, people per kilometer squared, and you can see that the Ganges Valley is very high. Has a very high population density, say, parts of the Indus Valley. Okay. GDP per capita, so income per person, how much money you make per person. And you see some of the poorest regions are here as well. I'm not sure globally, these are some of the poorest regions in Africa. And then we have agricultural land fraction. Also all of South Asia is very densely rendered agriculture. Why am I showing this? Because these are how are the agricultural goods being collected? There are workers out in the fields picking fruits or cutting vegetables and so on. Okay. So we have a sort of a perfect storm, as we like to say in English. We have poor conditions, outdoor conditions, and densely populated. We have extreme wet bulb temperatures, or extreme heat and humidity have high mortality rates. And this past summer in South Asia, there were some heat waves, and as well as following the news in the Middle East, Kuwait and Iraq were under very severe heat conditions. The combination of these factors makes the region very vulnerable to climate change and vulnerability. I think that's one of the key components of climate change. We have to look where do we want to spend our resources in terms of adapting to climate change. We have to look at vulnerability. So we set up a bunch of numerical experiments. And before I get into those, I just want to say that the IPCC, I think one main weakness of the IPCC, and this is slowly changing with them, is that they focus on that dry bulb temperature, the normal temperature we look at. So they're always looking at extremes in dry bulb temperature. It gets 50 degrees, but if it's 50 degrees dry, you can deal with it. You drink a lot of water, we stay in the shade, and so on. If it's 50 degrees with high humidity, we can lose our lives. So it really should be a combined measure of something like wet bulb temperature. The reason we like wet bulb temperature is because it's a very physical variable. It's very it's over something like the heat index, which is a parameter. Here's our set of experiments. This is the South Asian domain. We run it at about 25, in this case, 25 kilometers. These are done on workstations, or multiple core workstations. We have, I don't remember, 16 or 32 processors, so not that many processors. And we have three different scenarios to look at. It's historical simulations from 1976 to 2005, RCP 4.5, the business as usual scenario, which is RCP 8.5. We're looking at the period 2071 to 2100, okay? And the mitigation scenario, okay? Same period, 2071 to 2100. We're using boundary conditions from, so we nesting this model inside a global model. We're using boundary conditions from 3 global models. And we use the regional climate model that I was looking at the development time. Here's our Southwest Asia domain. So we have those 2 domains there that we're looking at. And let's first focus on Southwest Asia. Okay, this is our historical dry bulb temperature, 30-year maximum. So we just took the maximum 6 hours. Why did I use 6 hours there? So I took the 6 hours. We're getting data from these models about every 90 seconds. The time set on these models is about 90 seconds. So a minute and a half. And we're looking at 6 hours because that is where the fittest of humans, that's that sort of threshold. If you're exposed to 35 degrees for more than 6 hours, no human can survive. And you can see dry bulb, so this is just dry bulb temperatures, or regular temperature. And we have very high temperatures in the Middle East, which is expected. We know that. These are very low-lying regions, and we have cloud-free areas, so the temperatures can get very high there. And if we look at the business as usual scenario, we can see a lot of purple shades of temperature exceeding 60 degrees Celsius. That's pretty hot, right? If we look at the business as usual scenario, we still have some in the Tigris and Euphrates basins in Iraq, high temperatures, but it's much mitigated. We really stand to benefit from mitigation. But we're not interested in dry bulb temperature, let's say. We're really interested in wet bulb temperature. So here are the wet bulb temperatures, and we see in the present day scenario, as we expect, there aren't any exceedances of 35 degrees. And but we still have very warm temperatures, and the warmest temperatures are in the Gulf region, as we expect. Okay? And I'll talk about why that's the case, because anything you do in these types of studies, you need to answer why. So I can make all the projections I want, but I have to say why. In our future scenario, in the business as usual, we can see lots of exceedances of 35 degrees Celsius. Okay? So this means that these regions here, under business as usual, at least we are projecting these regions to see temperatures exceeding 35 degrees, wet bulb temperatures exceeding 35 degrees, which would result in mortality. Mitigation, again, we see the region really stands quite a bit to benefit from mitigation. And we pick different cities, okay, so I think some of you are familiar, say with Doha or Dubai, but you can't see Dubai, so we're focused on the different one. We can focus on the worst one, which is Padre Abbas in Iran, and we can see that on a fairly frequent basis that this red line right here is quite hard for you to see this, but this is wet bulb temperature. The red line is 35 degrees there, that horizontal red line. And this is the time series from 1980, basically 1976 until 2100, okay? So you can see in this red part, which is the business as usual scenario, we're exceeding the 35-degree threshold on, say, every 5 to 10 years or so. Okay? Other regions like Kuwait, very hot regions, but very dry. They have these winds that come from the northwest that dry the air out. Places like Doha, okay, they approach it, they may exceed it. Okay? Abu Dhabi, okay, a rapidly growing region right here, exceeded it several times in the simulation. Okay? Mitigation, okay, so what you'll notice is none of these green lines ever cross the 35-degree line if we mitigate. We do something about our emissions. Another aspect is that the 31-degree events are to be exceeded in most summers regardless of mitigation. Okay, so these extreme danger events that our national weather, or the U.S. National Weather Service calls extreme danger, those are projected to be exceeded no matter what. We look at histograms, which I'll just summarize this because it's hard for you to see, I think. But if you look at sort of a PDF, a probability density function, or just histograms of the data, we see that this is looking at sort of these numbers there are the 95th percentile is saying that the hottest event of the summer. So like basically, a 5-day event over the summer. There's some sort of average event, maybe it's 31 degrees or something like that. Okay. That hottest day of the summer in the present climate is becoming like every other day in the future climate. Okay. So the average hot event of the summer, the hottest day of the summer, the hottest week of the summer is becoming like every other day. Okay. One day we have it, one day we don't. So even if we don't reach the threshold, it's still very worrisome. This came from a commentary on the paper that we had in 2016. This particular person looked at Banu Mashar in Iran, which is on the Persian Gulf, right here. Okay. So near Kuwait, which is very dry, but this region is very humid. Okay. And we see in 2015 that the 35-degree threshold was hit. It barely touched it, but it hit it on July 31st. Okay. So I think some people have accused climate change people of being sort of alarmist, but we were projecting this out at the end of the century, and we actually saw an event. It wasn't 6 hours long, but we saw a 35-degree event. So I think we might even see this sooner than we projected on the study. If anybody follows the news by waves, you see that a lot of regions, particularly in South Asia and the Middle East, are having these really extreme heat waves that are resulting in deaths. Why are we getting high wet bulb temperatures in the Gulf? I mean, it's a dry region, right? It is a dry region, except at the Gulf. Okay, so the deserts around it are very dry, but the Persian Gulf itself is very, very shallow. It's only like 50 meters deep on average. Shallow body of water. Okay, so it's very easy to heat that up. Okay. Let me back up. It's a subsidence region. What does that mean? We have high pressure there. Okay? High pressure means that we have no clouds. Okay? So if you're in that region, it's very cloud-free. Precipitation cannot form. So there's a lot of solar radiation coming in, which then causes warming of the surface. Okay? So we have very high dry bulb temperatures over that region. We also have shallow water bodies, which I stepped ahead and said. And these waters are very, the Strait of Hormuz here, they're very closed off. There's very little interaction with the Indian Sea here, both of Oman and the Persian Gulf there. Okay? So those shallow body waters result in very warm sea surface temperatures. This is present-day sea surface temperatures, over 32 degrees in the summertime. Okay? Imagine going and taking a swim in 32-degree water. That's pretty warm. It's like a broth or something. And you have 2 meters of evaporation over here, a lot of evaporation. Okay? Those two factors, again, I have a whole schematic of this looking at the energy budget and so on, but those two factors result in very hot, humid conditions and a potential for very high local temperatures. And we also saw a similar mechanism for the Red Sea. So this got published, it came out in October, about a year ago. It got a lot of media attention because the reason is because the Muslim pilgrimage